So let's look at this packet. Let's go to the front page here of this. So on our quiz that's going to be on Wednesday. Okay. So this packet. So did you get one of these? Oh. Okay. So this packet, we're only going to go up through page 16. Okay, we're not going to continue that for tomorrow. I got another packet here today I'm going to give you with some problems. So we're stopping at page 16, and you're going to hang on to it because after page 16 gets into some second semester stuff. So we'll come back to this packet, right? We'll be February sometime, March, we'll be digging out the motion packet again. You'll be looking in your notebook, right, trying to find it. And of course, that's after you've got like 13 other packets of things that you're saving. So you're gonna. That's why try to three-hole punch them so you can maybe keep track of them better if you have such things. But anyway, so up through 16. So, but we want to get those done. So we'll take some questions on some of these, and then we're gonna focus on this position, velocity, acceleration concept. For our quiz next week. Then we're also going to get into limits. So starting tomorrow, last half of class tomorrow, into Monday, we're going to be working more on limits. We're going to talk more about infinity. We're going to especially get into limits with asymptotes and infinity and how that all works. We're going to be doing some discussion about that. And then those are the two things the quiz will be on next week. Position, velocity, acceleration, and then limits. Okay, that kind of stuff. All right. So this idea of position, velocity, acceleration shows up a lot in the midterm, the final, the AP test, those kind of things. So I'm going to show you some questions from last year's AP test that relate to this. Okay, so in discussing motion, 3 closely related concepts we need to keep straight. These are position, velocity, acceleration. Now, what you're going to find out today is that when we talk about position, velocity, acceleration, it's very much the chart. The concepts of what we're talking about are very similar. The way we work the problem is very similar to information that we had in the chart. Okay? So, if x is the position of a particle along the x-axis at any time t, then the following statements are true. Initially means when t equals 0. At the origin means x of t would be my preferred way for you to write that. Now, if you just wrote x, that's okay. But x is the output here. Important to understand. At rest means v of t would be one correct answer. X prime of t would be another correct answer. They're both correct. And we need to understand that they are the same thing. That position, velocity, acceleration, if we're going to use the x-axis as our position function, then x prime will be the velocity and x double prime will be the acceleration. So we want to make sure we really understand that. Okay. Also, x prime could be written dx over dt, and this also brings into mind something we've talked about earlier when we're doing implicit. Think about the gateway test. When we're doing implicit differentiation, we said you don't have x primes, you have y primes, you won't have x primes. That's because we're doing it with respect to x. X prime would be dx over dx, which is 1. That's what the derivative of x is, it's 1. However, in this case, it's with respect to t. So the derivative of x over t, dx over dt. So there is such a thing as x prime here, because the x is something different. The x is our output, it's our position. If the velocity of the particle is positive, the particle is moving to the right. If the velocity of the particle is negative, the particle is moving to the left. To find average velocity over a time interval, divide the change in position. So average velocity would be x of b minus x of a over b minus a. It would not be, it's not velocity, as many of you I see you writing and erasing might have had velocity there. Average change in velocity is, or average velocity is change, because what you want is velocity for your answer. So you want meters on top and you want seconds on the bottom, so you get meters per second. So it's change in position. Remember, we said average rate of change. When we hear the term average rate of change, matter of fact, we hear the term average at all, we basically take slope between 2 points. Now, there's one exception to that later on, which we'll learn about, but for the most part, for us, we hear the word average, we're thinking slope between 2 points, and if you look at that, that's what it is. That's slope right there. It's the change in position divided by the change in time. Okay? Instantaneous, of course, is the velocity at a single moment. If the acceleration of the particle is positive, then what is increasing? Velocity. Now, again, it comes back to the chart. Acceleration positive means the velocity is increasing. Okay? If the acceleration of the particle is negative, then velocity is decreasing. Now, let's talk about velocity just a minute again. Velocity decreasing. Does that mean that the thing is slowing down? If velocity is decreasing, does that mean the thing is slowing down?
No, it could just be going less.
Well, no, less fast would be slowing down. It depends on direction. Okay, it depends on direction because. So let's think of this. Because velocity, remember, can be negative, right? So here's a particle that's going 10 mile an hour, 9 mile an hour, 8 mile an hour, 7 mile an hour, 6 mile an hour. That's its velocity. Is that velocity decreasing? Yes. Is it slowing down? Yes. Here's another particle. It's going negative 5 mile an hour, negative 6 mile an hour, negative 7 mile an hour, negative 8 mile an hour. Are those numbers decreasing? They are. The velocity is decreasing, but it is going faster, right? It's going 5 mile an hour, 6 mile an hour, 7 mile an hour, 8 mile an hour. It's going faster, but its velocity is going down. Okay, so that seems weird, because when we hear velocity, we think speed. And so, but then that velocity has direction. Yeah, but there's more to it than that, right? So velocity, so we talked about the velocity decreasing. That doesn't tell us whether the thing's speeding up or slowing down. Now, you'll see at the end today, one of the last things we do in these problems is we will be asking the question, is this particle speeding up or slowing down? And what you will find out is you need more than just velocity and you need more than just acceleration to know that. You need both of those. Okay? Because if I throw a ball into the air, its acceleration is negative all the time. Gravity is negative because it's pulling down. So when I throw a ball in the air, at first it's slowing down. But then when it starts falling, it speeds up. But the whole time its acceleration is negative. So people confuse, people think the word acceleration always means speeding up and deceleration means slowing down. Well, in our normal everyday talk, it does. But not for what we're talking about. We won't ever talk about deceleration. What we'll talk about is acceleration, and acceleration can be positive or negative. Okay? But just because it's positive or negative doesn't tell you if something's speeding up or slowing down. You need acceleration and velocity together to be able to tell if something's speeding up or slowing down. Okay, so we'll get to that later. All right. So anyway, but for position velocity, if the acceleration of the particle is negative, if acceleration is negative, then this is decreasing. Just goes to the chart. Okay, in order for a particle to change direction, the blank must change signs. The velocity must change signs. All right, now let's go through number 11 here. One way, and we'll see how you did on this one. My guess is this was not an easy part. This was hard. Okay, so let's go through 11 because this is an important problem. One way to determine total distance traveled over time intervals is to find the sum of the absolute values of the difference in position between all the rest of the points. Whatever. Total distance traveled. Total distance traveled. This is the position of the particle right here, from 0 to 6. We want to find the total distance traveled. Anybody got an idea? Come on, throw it out. What can I do? I mean, something. Plug in something. Plug in a number. Something. Wouldn't there be something that would seem reasonable to do? Put in a 0 and put in a. To me, that would be that's where I would start. Like total distance traveled. Well, that would be like the beginning and the end, right? That makes sense. The beginning and the end. So let's put in a 0 for t. So what do we get? Put in a 0. We get 4. So what's that tell you? right? So we better start here by just understanding what kind of problem we have. We have a particle moving on the x-axis. So what's that tell you right there, what we just did? No, not acceleration. I didn't say anything about acceleration. It says at 0 seconds, and here's the x-axis, particle's right there, right? Its position is 4 at time 0, at 0 seconds. We don't know where it's going, what direction, that's just where it is. That's what position means. That's where it is. 4 miles east of Bismarck, right? And then we could put in a 6. And what would that tell us? Where it is at the end, right? So there's where it started, and then this is going to tell us where it is at the end. Okay, somebody do that. It's 22. So it's way out here. Oh, so total distance traveled, 18. Right? Wrong. Right? Wrong. What do you think? Ella?
Couldn't it have moved left as well?
Okay. We don't know what direction it moved, right? Jace, I think, when I asked that question, Jace this morning, I said, is it 18? He said, no. I said, how do you know? He said, that'd be too easy. It can't be 18. That'd be too easy, right? This is calculus. It can't be easy, right? Could be 18, though. Couldn't the answer be 18? Could be. Could be if it started at 4 and went straight to 22 in 6 seconds, then it total distance traveled is 18. But we don't know if it went left or right, right? We don't know where it went during those 6 seconds. Did it go to the left for a while and then come back and zigzag back and forth, or what did it do? Or did it go past 22 and then come back, right? We don't know. I started here at noon. At 6 o'clock, I'm in Grand Island. Did I travel 45 miles? I don't know. Did I go to Lincoln and then come back and then I'm at 6 o'clock, I'm in Grand Island, or what, right? We need to know more. Okay, so now let's read what the problem said. One way to determine total distance traveled is to find the sum of the absolute values of the differences in position between all resting points. Okay, there's a lot of mumbo jumbo there. Let's focus on that. Why would it be important to find the resting points?
Those are where you change direction.
That's where if it changed direction, it had to have stopped, right? What's another name we had for resting points? And then stationary points. And how do you find stationary? How do we find the resting points? When the derivative, remember we had that up above, you had where does it rest? When the velocity is 0, which would be when x prime, so let's do it. So when x prime, which would be, bring down a 3, that'd be t squared minus 2t minus 3. Don't we want to know when that is 0? This is what we would do on a chart problem. If there's a local max min problem, this is what we do. But we're doing the same thing, but for a different reason. We're doing it now because we want to know when the velocity is 0. So that would be t minus 3. That would be t plus 1 equals 0. So that would be t equals 3 and negative 1. But we can throw out the negative 1 because we're only looking from 0 to 6. So this means at 3, did this thing turn around at 3? Is that what we just found out, that this thing, Allie, that this thing turned around at 3? What did we just find out? It stopped at 3. But we don't know if it turned around, right? So it might have been here at 4. So at 0 seconds, it was here. 3 seconds later, it stopped, took a little break, instantaneously, an instantaneous break, and then kept going to 22. Could have done that, right? But it might have went this way and then took a break and then came back that way, right? We don't know. So what do we need to find out?
Side change and
So a number line? Oh, look at this. It's just like we did with local max min. Then we do the derivative, set equals 0, put that number on it, put that on a number line. We could call this b or x prime, doesn't matter, it's the same thing. Put a 3 on there. So we got 1, we got 4. Let's plug it back up into here. 1 minus 3 is negative, 1 plus 1 is positive, negative times positive is negative. So this thing obviously went, no. What did I just say? Negative. Did those words just come out of my mouth? I said negative times positive is
negative being
Oh, did I say negative?
Yeah.
Oh, good. Well, that's not quite as bad then. Still bad, but at least I didn't say negative times positive isn't positive. Negative times positive is a negative. Now put in a 4, positive, positive. Okay. So this particle did what?
Change direction.
Right. And so it started out by going left, right? That's what that tells us right there. Went left, then it went right. Okay? So we're getting it somewhere. We're making progress. Now what do I need to do? So I know it went left. I got to go plug a 3 into the original, right? I got to plug that 3 into the original to see where it was when it stopped. I got to know where it was when it stopped. Now, so right here, find the sum of the absolute values of the differences in position between all the resting points. So we have the endpoints and we have where the derivative is 0. Well, that sounds familiar. Wasn't that list of candidates? We did the derivative. We took the endpoints. We took where the derivative is 0 and we plugged them back into the original. Isn't that what we're doing right here? Right? It's the same thing. Okay, so we need x of 3. Okay, so here are my endpoints. Now I'm going to plug in a 3. What do we get? Negative 5. So this thing, what this particle did is it went here, and then turned around, and it went back to there. So now what do we need to know? Well, we need to know it went from 4 to negative 5. Oh, 4 minus negative 5, absolute value, that's 9. That's what this is all about. The sum of the absolute values of the differences in position between all the resting points. In other words, you got to see how far it went. Now, you're not going to write that out like that. You're going to say, oh, how far is it from 4 to negative 5? How far is that? It's 9, right? So it went 9. And then it went from negative 5 to 22. How far is that? 27. So how was the total distance traveled? 36. Total distance traveled is 36. But we could do it. We could do it that way. We could say, okay, that's 27, right? That's what they're saying. The sum of the absolute values of the differences in position between all the resting points. Okay? And the resting points includes the endpoints, right? But in a sense, what did we do? We did the derivative, set equal to 0. We made a list of candidates, our endpoints. But I wouldn't call it a list of candidates. I wouldn't think of it that way. This isn't a max min problem. I mean, that's not how this is phrased. We just got to think through the problem, what we're doing. Okay, that's total distance traveled. Now, what if we would have just taken x of 6 minus x of 0 and gotten 18? It would have been wrong for this problem, but that does have meaning for us. In science class, you call this something that starts with a D, the difference between the beginning and the end. Displacement. Heard that term? Also, in this time, it would be net distance traveled. That's a term I would use. So total distance traveled is what we found here. Net distance traveled would be 18. That's the net distance traveled, or displacement. We just take the beginning and the end and we subtract. Now, that could be negative. Total distance traveled is always going to be positive. Okay? But displacement could be negative. If you start at 9 and end at 1, 1 minus 9, that's negative 8. Your displacement would be negative 8, or your net distance traveled. Okay? All right. So, doing very similar things then that we've been doing, but yet now in a new context, particle motion problems. This is what we want to work a lot on here. Okay. What do you have? What questions do you have on the next page? I just want to take a short amount of time here to answer a few questions here. But because there were some of these. Now, I would ignore number 4 here. Is there a guaranteed time? Number 5 on the next page, is there a guaranteed time? We're going to get to that later in chapter 4. So if it made sense to you, fine, answer it. If not, don't worry about it. Okay? But is there something else on this table problem? Any of these that you were wondering about? What about number 3? What'd you do here for number 3? On page 7. V prime of 10. How would you do V prime of 10 here?
Find R sub t, and then maybe put in prime of that, because that just looks like it's.
Well, I don't. I'll be honest. Most of the time, we don't want to get into that as far as figuring out what the.
Oh, we don't have any y values.
Yeah.
I did it the wrong way. Like the wrong word.
like I did x of 12 minus x of 8 over 12 minus 8.
Yes, but it wouldn't be x of 12.
Or
It would be v of 12. Yeah.
I-
Now, I wouldn't call that the long way, but I get what you're saying. Slope between 2 points. That's all you can do. When we have a table of values, the best we can do is the slope between 2 points. And they want, this is v, they want the slope of v. So that would just be those 2 points. So I love what you said there. Matter of fact, I want that, that's what I want everybody to have on their paper for number 3. I want you to have that right there. That's what you should have. Because this is meters per second, and then this is seconds, and v prime should be acceleration, right? That's meters per second squared. So, right, v prime should be acceleration. So if we want to find the slope at 10, 10 is right in between those 2 points right there. So we'll do the slope between those 2 points. Now, that would be 5 minus 7 over 12 minus 8, which would be negative 2/4, which would be negative 1/2 meters per second squared. That's what we would want to have. And that means, and it says describe what's happening in the context of the problem, that means the acceleration is negative, which means the velocity would be, the acceleration is negative, it means velocity is decreasing, which of course it is. Here the velocity is decreasing. So, okay? But yes, this is the kind of, it's just a lot of different ways of saying different things that we need to be able to look at. Is there a time in here when the particle's at rest? Yes or no? When? Sometime in here, it's got to be, right? Because the velocity is negative, switches to positive. Sometime in there, it's got to be 0. Sometime in here, the velocity's got to be 0. Now, I don't know about here. It might be, but we don't know. We can't tell for sure. But here, we know for sure. Now, here's another word that we're going to get into this more in chapter 4. Differentiable means a derivative exists everywhere, so it's nice and smooth, no sharp points. So that's how we know it can't jump. It can't jump from negative 3 to 2, right? It's got to go through 0 because it's nice and smooth. So the key word there is differentiable. The function's differentiable. Okay, so it's nice and smooth. So yeah, the velocity's got to be 0 sometime. It's the only way you can go from a negative to a positive is to go through 0. Okay, stuff like that. All right, then you got a graph. Here's a graph. Again, same thing right here. Average acceleration. So Claire, you and I have the same thing here. Average acceleration is the same as saying an estimate of v prime. So this should be v of 4 minus v of 2. And this is confusing sometimes because you see the word acceleration, you think you should be using a. No. Average acceleration means, remember, the word average means slope between 2 points. So this is meters per second over seconds. That'd be meters per second squared. Meters per second squared. Okay? So v of 4, so you can just read those right off the graph. V of 4, you can get off the graph. V of 2, you can get off the graph. Okay? All right. Okay, so part of your homework is if you have not spent some time, now we're going to get into, we're going to spend a lot of time doing problems like this, so this is going to seem a lot easier, more familiar for you if you weren't able to understand what it was. And number 4 here, find the total distance. This is just like number 11 on the front page we just did. Find the total distance traveled by the particle from 0 to 5. It's just like number 11. Make yourself a little note if you didn't get it. That's just like number 11 on the front page. Okay, so you want to, so we need to go back. So part of our homework is to go back and finish this through page 16, and then I'll take some more questions on it. Okay, if you've got some more. Okay, through page 16. All right, let's move along to this thing then. some of your work, oh geez, this is very similar to that problem we were just looking at on page 9. I should have told you. Very similar, so most of your work for this, you could actually translate over to there as well. But anyway, don't look at that, let's go through this one together. Okay, this one asks some different questions though, so you're still gonna have stuff to do. Okay, so we have position of particle moving on the x-axis given by this equation. And we're using the interval 0 to 5. We have seconds, x is in meters. Okay, so let's just go through this. Let's just go through this, work through this. Oh, wait, time out. Well, no, we can do this. I forgot I was gonna do something else. I was gonna show you something else first, but that's okay. We'll come back to that here in a minute. So we'll go ahead and finish this problem. So find the velocity at time t. Okay, what's that mean? What are we going to do? We're just doing the derivative of the x function, right? So x prime of t, you want to call it v of t. Matter of fact, it's even good to write them both. But either one, I don't care. Put v, put x prime, okay? And so that's going to be what? 3t squared minus 12t plus 9, right? And then you're done. At time t, so that's all I want. Okay? What is the velocity after 2 seconds and after 4 seconds? So what do we have to do there? And I want you to write that. I want you to get in the habit of writing that. I want you to write v of 2. I want you to write v of 4. Because here's what. It's communicating to me as I'm grading something that what you're doing. So if you make a mistake, your chances of getting partial credit are much higher. Okay? So I can tell, oh, he's taking a 2 and he's plugging it into this equation. Okay? All right. And what do we get? -3 meters per second. Anytime the problem's got units in it, you should put units on. Okay? Oftentimes there are points awarded in the problem for proper units. Now, a lot of times we try to specifically state that in the directions, but not always. Okay, so you should put on units. Okay, what's 4? 9 meters per second. Okay, now what's that tell you right away? What did that just tell you about this particle? What's happening to this particle, right? What's this particle doing right now? At 2. Going left. This one? Going right. Now sometimes they'll talk about a particle on the y-axis, and so then your equation is y of t instead of x of t, and then it's up and down. Positive is up, down is negative. But most of the time it's horizontal motion, but it could be vertical motion too. When's a particle at rest? When v of t is 0. A lot of times I just do that right there, or I'll just write x prime of t equals 0, especially if I'm using my calculator. Now, notice at the top this says that this is no calculator, unless you need a little help, like there when you plug in a 4. If you want to use your calculator to plug in a 4, but I'm just telling you, these problems would be on a no calculator situation. But if you want a little help doing the computation, that's fine. Okay, all right. So what I'll often do is just write this, right? If it's a calculator problem, I'll just write out this, and then I'll go to my calculator to solve. Okay, I don't have to write out the whole thing. Okay, but here we probably will. So we'll probably take out a 3. T squared minus 4t plus 3 equals 0. T minus 3, t minus 1. So polynomials work really nice for this stuff because we can factor them nicely. They're easy to solve. You're going to have one tomorrow that's not a polynomial. So it's going to be a little messier. It'll be a quotient rule. You're going to have to deal with that a little bit. But you get t equals 1 and 3. And that'd be seconds. Wouldn't hurt to put that on there. But so when is a particle at rest? At t equals 1 and 3. Okay. So this thing is stopped 2 different times. Maybe it turned around, maybe not. Right. Well, so that leads us to the next question. When is it moving to the right? Number. Okay. So we're going to label it. We're going to make sure and label it. We're going to put a 1 and a 3. Now. A lot of times you're not going to have parts A through H, you know, they're just going to give you this and they're going to say, when's it moving to the right? And you'll go through all these steps, right? You'll do the derivative, set equals 0, do your number line. All right, so here we go. We got a 0, we got a 2, we got a 4. Put a 0 into here, negative, negative, that makes positive. Put a 2 in here, that's, remember, we're putting it back into V here. Put a 2 in here, that's negative, that's positive. Put a 4 in there, everything's positive. Okay, so what would I say for my, whoops, why did I just write 4, jeez. I am, a little bit. All right, what would I say here? When's the particle moving to the right? 0 to 1, 3 to 5. Because remember, our problem only goes from 0 to 5. So we wouldn't say infinity in that case. So from 0 to 1, from 3 to 5. The particle's moving to the right. So it did change directions in this case. Okay? All right. Find the displacement of the particle during the first 5 seconds. How do we say to get that? X of 5 minus X of 0. The end minus the beginning. Displacement. Change in position. Okay? So, and again, if you write that down, you can just go up above to the original, put in a 5. You guys do it. Give me what you get. How much? 20, isn't it?
Yeah.
20. Put in 0. I seem to remember 20. Unless we do that. And that's meters. Right? 20 meters. Started at 0 and went to 20. Okay? Started at 0, ended at 20. That's a displacement of 20. Find the total distance traveled. Okay, so that's what we just did on the front page of that other worksheet. So what additional information do we need?
X of 1.
We need X of 1
And X of 3.
and X of 3. When it stopped, we need to know where it was. So what we know so far is it started at 0, and we know it was at 20 at the end. That's what we know so far. Okay, that's all we know. So where is it at 1? So we plug that in, and what do we find? What do you get? How much? 3?
4.
I think it's 4, isn't it? I think it's 4. So it started at 0, and then it went to 4. So that's what we know now. And then plug in a 3. Isn't it 0? It's 27 minus 54 would be negative 27 plus 27. 0. So it went from 0 to 4, and then at 3, and then it went back to 0, and then it went back to 20. So total of 28 meters, total distance traveled. So it started at 0, that's what we found here with X of 0. Then it went to 4 at 1 second. Then it went back to 0 at 3 seconds, and then it went to 20 at 5 seconds. Okay? Total distance traveled of 20. Find the acceleration at time t. How do you find acceleration? X double prime. Or V prime, if you want to call it. I don't care. Any one of those 3. That's acceleration. X double prime, V prime. That would be 6t minus 12. And then, so that's acceleration at time t. And then after 4 seconds, that would be a of 4. And that would be 12. So you plug in a 4. 12 what? Meters per second, or meters per second squared, either one. I like to say meters per second, I think that makes more sense. If you write it, probably easiest to just write meters per second squared. Okay, now the last one is the thing we were talking about earlier. When is the particle speeding up and when is it slowing down? Okay, well, we already had a number line up here for V. I'm already erased, or I had to erase it, but my V number line was this, right? And so we had positive, negative, positive, right? So that's when it was going right, left, right. But what we got to figure out is when it was speeding up, slowing down. Okay, so what other information do I need? What did I say earlier? We need acceleration. We need to know when the acceleration is positive or negative. Basically, it's this, guys. This is what you got to remember. For something to be speeding up, velocity and acceleration have to have the same sign. Okay, so let's think about that ball getting thrown up in the air again. When I throw the ball in the air, the acceleration is negative. It stays negative the whole time. Gravity is negative acceleration. So the ball's thrown up in the air, acceleration is negative. On its way up, what's the velocity? Positive. So what you have is a positive velocity fighting against a negative acceleration. This ball is slowing down. But on the way down, what do you have? Velocity is, on the way down, velocity is negative, and the acceleration is negative. They're working together. So the ball is falling this direction, and it's being pulled this direction. It's going to speed up. So when velocity and acceleration have the same sign, they're working together to speed the object up in that direction. When velocity and acceleration have opposite signs, they're working against each other, and you have the ball slowing down. That is how you determine speeding up and slowing down. So what information do we need here to help us answer this? Another what? We need an acceleration number one. So we need to take A of t and set it equal to 0. So 6t minus 12 equals 0. Now that'd be t equals 2. Well, that's how we did inflection points, if you remember. Okay? Well, if you look at a velocity graph and you want to see if something's speeding up, or a position graph to see if something's speeding up, it's when it's concave up and increasing. Well, think about it. If something's concave up and increasing, it's going faster and faster. Well, what's happening? Its second derivative is positive because it's concave up, and its first derivative is positive because it's increasing. Well, there you go. The velocity and acceleration are the same. That'd be x prime and x double prime. Or if you have something going down and dropping faster and faster and faster, what do you have? You have its derivative negative because it's going down, and its second derivative is negative because it's concave down. So those are the two situations when you would have something speeding up. If it was doing this, or if it was doing that. Well, in both of those cases, x prime and x double prime are both positive here, both negative there. Okay, so they go together. All right, so we need a number line at 2, and if you put a 1 in, here's your a prime right here, or a double prime, or excuse me, your x double prime, your a equation. If you put a 1 into here, you get negative. You put a 3 into here, you get positive. Okay, so now we're going to take this number line together with this number line to answer this question now. All right, so speeding up. Speeding up. Slowing down. Let's start at the beginning. That's usually easiest. So let's start at 0. What's happening? Velocity is... No, not increasing. Velocity is positive. Acceleration is negative. What's that mean? So at 0, it's slowing down until when? Till when? I've heard 1, I've heard 2, I've heard 5.
2.
acceleration is negative until 2. But at 1, what's the velocity do? Changes to negative. So after 1, the velocity is negative and the acceleration is still negative. So what's happening? It's speeding up. So this is slowing down from 0 to 1, and it is now speeding up from 1 to 2. Because until 2, acceleration's still negative, and you're still in here on velocity is still negative. They're both negative. They have the same sign, still speeding up. But after 2, what's acceleration do? Changes to positive. Now, you have velocity. We're at 2 now. We're after 2. Acceleration's positive. You still have velocity negative until when? Until 3. So this is slowing down from 2 to 3. But after 3, now the velocity's positive, and you also have acceleration positive. So now that means they're the same sign, so they're now speeding up until 5. Now, maybe it would make more sense if you stack these on top of each other, maybe, right? If you took a velocity graph, an acceleration graph, and you stacked them on top of each other. Maybe something that would look like this, okay? So I kind of hesitate to show you this because it can get a little more confusing, but we could put our 2 in here, right? And I don't know, you'd almost have to use different colors, I suppose. But your velocity goes positive, negative, positive. Your acceleration was what? Negative, positive, like that. Okay, so when are they the same? When are they different? When are they the same? So they're different until here. So that's slowing down. They're both negative until here. Then they're different here. And then they're the same after that. You know, so maybe kind of an overlapping kind of a thing there could be something you want to do. It's kind of up to you. All right. So I'm going to tell you what other problems. We're not going to do all the problems in that packet just yet because I want to save some for next week when we're reviewing for the quiz. It'd be a good time to save some. So I'll tell you which ones here in a minute. If you would just get your notes out just for another 5-10 minutes here, I want to show you a couple of problems. Just a place in your notes where you can jot down maybe a couple things here on a couple of problems that I've got. I just want to show you a couple problems off of last year's AP test. Okay. Actually, I'm going to show you one problem off of last year's AP test, and then I'm going to show you a problem off of one from a couple of years ago. So this was a test that Kearney High students took last year, all people in the U.S. There's actually 3 different versions of the AP test. The regular one everybody takes in the United States. There's a makeup exam for people that have a conflict on that date. There's an international exam because of the differences in time zones. There's an international exam again. But this was from the normal one last spring. This is number 17. This is in the no calculator part of the test. Okay, so go ahead and read that question. All right, what do you suppose you're going to do to start this one? Do the derivative. So you have a particle motion, you got position function, they want to know about velocity, so that's a derivative. So we're going to do x prime. Okay? How are we going to do x prime? What do we need to do x prime? We need what? Well, right, but how do we do the derivative? See, this is part of the problem. This is maybe why we only had 33% pass the gateway test, because do the derivative just meant do the derivative. How are we going to do this derivative? The product rule. We need the product rule, right? So 12e to the negative t times sine of t. Okay, so what's derivative of 12e to the negative t? Well, you're going to kick out a negative, right? But otherwise it's its own derivative. Sine left alone plus 12e to the negative t left alone. Derivative of sine is cosine, right? Okay? And then what? It says when is the first time when the velocity is 0? So we're going to set equals 0. This was a no calculator problem, okay, on last year's test. Okay, so what do we do next? You could, you mean this whole term here? Add this whole term over. Okay, I might suggest one thing first before we do that. Take out a 12e to the negative t. I think that's a safer bet to do all the time. And I'll explain myself here a minute ago. We talked about this when we did that thing on solving equations. Okay. If I add that over, you might be tempted to divide a 12e to the negative t and to cancel them, and then that's always trouble. If that's ever 0, you lose potential solutions. So I don't like doing that. I always want to factor something else first before I start moving things around. Now, it turns out we'd be okay on this one, because now, when are those equal 0? When's this equal 0? Now, if you put a 0 in there, e to the 0 is 1, so that'd be 12. It's never 0. So it turns out in this particular case, we could have divided by it and been okay. All right, well, that's never 0. So now all we have to do is solve this. Okay. So when does this equal 0? Now I would suggest adding the sign over there. And we get cosine t equals sine. And the nice thing is, it says t's positive. And it says when's the first time. So when does cosine equal sine the first time? At pi 4s, right? Right here. So there you go. So notice, and this is a great example of what they do, especially in the no calculator multiple choice section. They sneak in some trig on you, right? You got to know how to do derivative. You got to know product rule, right? So you got to know that. You got to understand, of course, the basic thing we're talking now. The derivative of position is velocity, so you had to know that. But you get some practice on product rule, and then you got to know some trig. Okay, pretty typical kind of problem. All right, we're going to see a lot of those, and by the time you guys get to the midterm, and then hopefully by the final and the AP test, these will be easy, easy, easy. Okay, problem is we'll have been away from stuff like this for a while, and then coming back to it, we'll have to review. Okay, then I want to show you, this is from the 2015 international exam. Let's look at number 83 real quick. I just want to show you this because you don't have to write anything down on this one. This is from the calculator part of the multiple choice. So go ahead and read number 83 here. Yes, that's a good question. Okay, so what are we going to do there? So this is x prime, right? Which is velocity. So what they've told you that x is the position function, but what they gave you was x prime, which is velocity. So we're going to do the derivative of it. To get acceleration, we're going to do the derivative of it. Okay, so negative, now this is a calculator one. You could let the calculator do it for you. I don't think you need to for the derivative. But you're going to do that, and then it says, and then what are you going to do? Set it equal to 0, and then that's when you pull out the calculator and do a solve, because that's what they intend you to do. Obviously, with the decimals and everything, you can tell that. But you would just do a solve on that right there. Okay? So again, another type of problem falls right in line with the things we're talking about right now. Okay, and now I want to go to the multiple choice section, and this is problem number 26, okay, and go ahead and read that one. Okay, now what's different about this problem? They want to know the distance traveled, which means we need to know x of t, right? Because we want to see where it was at certain times. But they gave me x prime, v. So how are we going to get x of t? We're gonna do the antiderivative. Now, one of your problems today is gonna be that way, where you're gonna start with the velocity and you have to go backwards, okay? So, let's do the antiderivative. 2 will just hang out there. What's the antiderivative cosine? Just sine, right? The derivative of cosine is negative sine, but the antiderivative is just sine. And what do we do with that 3? Take out a what? A 1/3. So this is going to be 2/3 sine of 3t. And then the other thing we need to remember is there's a plus c there. That's going to be important today. Now in today's problem, we would then find the c. In today's problem, I would give you some more information then. I would tell you something like this. An initial condition. I would say an x of 2 equals 5, and then you plug a 2 in here, plug a 5 over here, and you would find your c value. Turns out it's not going to be necessary on this one. You'll see here in a minute. Okay, so but I'm going to leave the plus c on there so you recognize we have to do that. Now, just check this. 2/3 would hang out, derivative sine's cosine, kick out a 3, the 3 would cancel that 3, we'd get 2 cosine 3t. Okay, seems to check. Okay, so that is our position. Now, what was the distance traveled from 0 to the first time that it stops? Okay, well, we can plug in a 0. Okay, let's put a 0 in there. What do we get? Sine of 0 is 0 plus c, so this would just be 0 plus c, or just c. And then we need to figure out x of what? When it stops. Oh, how are we going to find when it stops? We're going to have to set that equal to 0. So we're going to come over here, we're going to set that equal to 0, divide by 2. That would just be that. And when does cosine equal 0? Cosine is 0 at pi halves. So that means in here has to be pi halves. So 3t has to be pi halves, right? So t would be pi 6. Oh, and this is what happens to a lot of people on the AP test. Oh, pi 6. Hey, there we go. No, that is not right. They always throw those distractors in there, and you get it, and you think, no, that's not what we need. We need the distance traveled. What we just found is when it stopped. Pi 6. That's what we need to plug in over here. That's what we were doing on that other worksheet, right? How far did it travel? Well, we got to check at the stopping points. So the first time it stops is pi 6. So we need to plug a pi 6 into this right here, right? So put a pi 6 right there. 3 times pi 6 is pi halves. What's sine of pi halves? Sine of pi halves is 1 times 2/3. This would be 2/3 plus c. Now here's why the c doesn't matter. So it started at 0 plus c, whatever that is, and then it went to 2/3 plus c. How far to go? 2/3. It doesn't matter what the c is. The c it's like if you subtract these, the c would just subtract that. So that's why it didn't matter. Okay. So the distance it traveled is actually 2/3. Okay. All right. So that's a pretty tricky one there, but that would get easier because we're going to see this over and over. We're going to keep seeing these kind of problems. Okay. Here's what I would do for tomorrow on the worksheet. First of all, the packet from yesterday, get through 16. Get through page 16. Okay? On this packet, I would suggest doing number 2 and number 3 on the next page. Number 3 is a little more challenging. The derivative is going to be a little more challenging for you. Well, it shouldn't be very challenging, but then solving it, you have to think a little bit more. A little harder than these polynomials. Okay, so I would do 2 and 3, and then I would maybe skip to 5. And what is it about 5? What function do they start you with on 5? The velocity, v. So it's like the one we just talked about. So you're going to have to do something there with that. I would do that. Then I would leave 4 and 6 and 7 for practice next week when we get closer to the quiz. Okay, so let's finish that other packet, and let's do 2, 3, and 5, and for each of these back here, you're answering these questions here. Okay? So for each one of those, that's what you're answering. It's this set of questions. Okay? 2, 3, and 5, plus the other thing, and then study for the gateway. I'll be in the two pieces.
The ones that I highlighted, the ones, everything in the table are, what we got.
Do it, you're cool. Do it.
I said one of these is not
Yeah.